Alright guys, welcome to our new unit. This one's all about rational equations. We're going to start off with graphing. So our EQ for today, what part of a rational expression tells you where asymptotes are located? So go ahead and pause for a moment and write down your EQ. Now I know what you might be thinking, there's a lot of stuff in this question that I have no idea what it is, but that's okay. We're going to break it down and we'll see that some of it's fairly familiar, right? So what part of a rational expression? Well, we've taken a look at kind of rational expressions. That first root of that word is ratio, right? And we took a look at rational exponents before. Well, that meant we dealt with fractions that were exponents. So it's the same thing here. Rational exponents is just anything with a fraction. So I'm going to start off with a fraction that's really basic, like 1 over or something. To find out what I'm going to put in that something for these kind of expressions, I'm going to define this term rational function. It's a function where the variable is in the denominator of a fraction. So that'd be like if I had 1 over x. And this just happens to be the most basic kind of rational function. So we could call f of x 1 over x. Okay? Now, the other part of this question that might seem a little weird is this word asymptotes. And I get that. Yeah, we haven't heard of that. Yeah, it's a funny sounding word, asymptotes. Let's go ahead and find out what those are by actually graphing a rational equation. Alright, so we're going to start by graphing the parent function, which is always going to be the most basic kind of function of that type. So in this case, the most basic kind is indeed 1 over x. So let's go ahead and plug in some numbers. I want easy numbers to work with, but I want to see what's going on when I have some negatives. So if I plug in negative 2 in for x in my denominator, I get negative half, right? And if I plug in negative 1, 1 over negative 1 is just very simply negative 1. So let's go ahead and plot those 2 points right now. We've got negative 2, comma, negative 1 half. Negative 1 half is just some number between 0 and 1. And then I've got negative 1, comma, negative 1. Okay, next couple of points, or the next thing I want to see is, hey, what happens at 0? So if I plug in 0 into my denominator, this looks really weird, right? Usually because we don't see it, because we say we can't divide by 0, and that is undefined. That's a big fat no-no. Okay, what that tells us is that this function, we cannot have x equals 0. It's an excluded value. Okay, we can't have our functions be undefined. Next, let's go ahead and look at the positive numbers. 1 divided by 1 gives us 1, so our next point is at 1, 1, right over here. And then we have 1 over 2, and that's a half, so we have 2 comma 1 half. Now, this seems a little bit weird. What is this shape going to look like? How am I going to connect those? Kind of looks like it would be a parallelogram, right? Well, that's not. That's more of a geometry thing, not an algebra thing. So, we're going to go to Desmos.com and take a look and see what does this function look like. That way, maybe we can figure out what the pattern is supposed to be. Alright, so Desmos.com, we've seen this before. This is just an online graphing calculator, and I'm going to graph the function y equals 1 divided by x, that parent function. And now you start to see this. This looks really weird, right? This is different from anything we've seen in algebra so far. Well, this is something called a hyperbola. Okay, and so what we want to notice about this is that we've got a couple of points, and here I see this point is my 1 comma 1 point, and then I even have this 2 comma 1 half point, so that matches, and I have negative 1, negative 1, and then I have negative 2 comma negative a half right there. But it looks like it's going on forever straight up, and then it's going to the right forever straight out. Okay, but it's got this nice bend, and then there's another one here. So interesting that all the points don't actually connect. But it will pass the vertical line test if you look. So that's something that's really interesting. We'll find out why it's splitting like this and going in those directions. So let's go back and try and figure out how we can recreate this pattern. Alright, so what I want to do now is try and recreate exactly what I saw on Desmos. So I want to look and see what happens when I pick bigger numbers for x, because that's where I saw things running out to the right. So a number that's bigger than 2 would be, we can try 3. Okay, and then when we plug 3 into the denominator, we have 3 comma 1/3. Now, 1/3 is smaller than 1 half, so it's a little bit closer to the axis. And then what happens if I choose 4? 1 divided by 4, 1 divided by x, and that's again getting a little bit closer and closer still. Well, how do I get those ones where it's now going straight up? How do I get that part of the pattern? Well, let's pick some number that's in here between 0 and 1. Now, a number between 0 and 1 would be a half. So, if I plug 1 half into the function, I have 1 divided by 1 over 2. Seems really gross, but not that big a deal. All we have to do is divide fractions by multiplying by the reciprocal. reciprocal of the denominator is 2 over 1. 1 times 2 over 1 is just 2. So the next point I have is 1/2, comma 2. And now you can start to see where it's starting to bend upward. And if we do one more just for kicks, if I do 1/3, and we can start to see that pattern that 1 divided by 1 over 3 is going to give me the reciprocal of 1/3, and that's 3. And there we've got it. So now what we're going to do is actually we can start to see that nice bending curve, and we'll go and connect the dots. Alright, so you notice the way that I drew this curve, it's never actually touching any of the axes. It's going up and it's going to come kind of straight, but it's never going to touch the y-axis. And then when it comes down here, going further to the right, it's never going to touch the x-axis. Same thing's happening with this lower curve on the left. It's never going to quite touch the x-axis, and it's never going to quite touch the y-axis. Well, why is that? It's because we have these things called boundaries, which we will draw with a vertical dotted line here, and a horizontal dotted line here. And these are these things called asymptotes, okay? They're like a force field or a shield or a boundary, okay? It's a barrier that the graph can't touch or cross. Well, why can't we actually touch it? Why do we have this boundary here? Well, if we take a look here, what is the x value right here on this dotted line? That's the y-axis. The x-axis, that x value is 0. And what did we say about when x equals 0? We said that y is undefined. Okay, so this asymptote right here is telling us that it is undefined. So there we would have what we call our vertical asymptote. Now what about this other one? What about this horizontal one? Why do we have this horizontal asymptote here? Well, to illustrate that, let's think about some other points that we could pick for x. For example, I could pick some really big number for x. Let's say if x equals 10, then what does y equal? Well, y is going to be 1 divided by x, or 1 over 10. So that's another small number getting closer to 0. What if x equals 100 though? Then that means my y value would be 1 over 100, and x equaling 1,000. So I'm way far out on the x-axis now, right? I have a really, really big number for x. It's way, way off the screen here. But my y value is 1 over 1,000. As you can see, that number is really, really small. That's like 0.0001. It's really small, not quite even to the x-axis though. It doesn't actually touch it. And no matter what value we pick for x, we are actually never going to be getting down to that x-axis. Okay? And that's the exact same thing that's happening here. The smaller we get for x, the closer we get to this vertical asymptote, but we never actually quite get there. So now we can formally define these things called the asymptotes. And we say it's a boundary for a function. It's a dotted line that the graph will never actually touch or cross. And the nice thing about these asymptotes is we can see where these asymptotes are when we see what the form of our equation is going to be. So, we have asymptote form of a rational equation, and that's given to us right here. We have y equals a, which again is like our vertical stretch. We have x plus or minus h, and plus or minus k. And why those values are important, just like before they tell us about transformations, they're also going to tell us where exactly the center of our asymptotes are going to be. Okay? So now we know what the equation looks like in general. Let's go back and talk about domain and range and talk about the equations of these asymptotes, because these are all things that we are going to want to identify every time we look at a rational equation. So when we look at our parent function, we had a, if we were to think about this in terms of h and k, I'm really not adding or subtracting anything down here in the denominator, and I'm not adding or subtracting anything out here. So both my h and k values are 0. So what that tells me is that my vertical asymptote, I can write out that equation, as x equals 0. And then my horizontal asymptote, which I'm going to start abbreviating these as VA and HA, is going to just be very simply y equals 0. So that's true for the parent function. Now these asymptotes are going to move around, but here's something that we can see about our domain and range. For the domain, we really only have one value that x cannot equal, and that's where the asymptote is located. So it's real simple. Once you've identified your vertical asymptote, you know that the x can be any number. It's going forever to the left and forever to the right, but it cannot be 0. So we say x cannot equal 0. And then for the range, it's the same kind of idea for y, but we look at where's our horizontal asymptote, and that's right here, y equals 0. And that means that there's no way at all in this equation that y can ever be 0, so our range will be y cannot equal 0. So we want to identify these things, the vertical asymptote, horizontal asymptote, domain, and range, and we'll start to see the connections when we do some examples. So let's go ahead and take a look at a few of those after we talk about how we can also describe transformations of these. So transformation rules are really nothing new, you guys. We have A, H, and K in charge of shifting, stretching, shrinking, and reflection, right? So we have our vertical stretch, A. It's the absolute value of A specifically, and the nice thing is we're just going to kind of estimate what this is for these functions. We're not going to be looking at too many points and too much multiplication. What we want to focus on really is just sketching these. The asymptotes are the key things that are really important for us. Now, the larger our stretch is going to be, the larger the A value, the farther from the asymptotes these curves are going to be. So that just kind of tells you if we have a big A, don't make your curves too close to the asymptotes. They're going to be a little bit further. And we'll see what this looks like in some examples. And then negative A, H, and K, they all mean the same thing. A couple of things I want to point out to you. H is always going to be the location of the vertical asymptote when we change its sign. So x equals negative h is the location of the vertical asymptote. And then y equals k is going to be the location of the horizontal asymptote. So just like all these other graphs that we've done before, we want to identify the a, h, and k. And then we want to make our moves based off of our parent function. And so what are the parent function points we're going to use? We graphed a lot of points on that parent function, but I don't want to mess with all those. I want to make this simple. So now that we know at least the shape, all we really need are 3 points. We need to know where the asymptotes are located, and then we need to know 1 point on one side of the asymptote and another on the other side of the asymptote. So we're going to use these points, the easiest ones to work with, -1, -1, 1, 1, and then where we had that thing undefined. And this is going to help us out finding the location of the vertical asymptote. All right? So let's take a look now at some examples. So here's our first example, y equals 1 over x minus 3. So the first thing I notice, there's a 1 in the numerator, which is my a value. So if a equals 1, that means there's no vertical stretch, there's no reflection, nothing like that. Am I adding or subtracting anything down here with the x? And the answer to that is no, I'm not adding anything there. So my h value is 0. And then I have k. That's pretty obvious, that's the one that's not in the fraction, and that is -3. Okay, so since h is 0, I'm not doing anything to my x values. My y values, I'm going to be subtracting 3. We follow the rules with k. So my -1 minus 3 gives me -4, and then 1 minus 3 gives me -2. So the points that I'm going to plot are -1, comma -4, 0, undefined, which is again the location of one of my asymptotes, and then 1, comma -2. So let's go ahead and plot those points. So plotting those points, -1, -4 is going to be right down here, and then 1, -2 is going to be right here. And again, this can be kind of hard to see exactly what's going on. So what we need to do is we need to identify where those asymptotes really are. My vertical asymptote, as we said, is at x equals -h. Well, that means -h, there was no h, it was 0, right? So I'm going to draw a vertical asymptote when x equals 0, which is right along the y-axis, okay? So we'll go ahead and draw that in with a vertical dotted line right through the y-axis. Now, what about my my horizontal asymptote? Horizontal asymptote was at y equals k. My k value was -3. Okay, so when y equals -3, which is right along here, right smack in between these 2 points, I'll have another asymptote, but this time it's going to be horizontal, going from left to right. Okay, so now we have that. We have our asymptotes, and we can see where we're going to have these. And again, this is kind of like the apex of the curve, right where the bend is supposed to happen. So I'll go ahead and draw that image, and we'll see what that looks like. Alright, so there is our curve of this first example, and we'll go ahead and finish out by writing out the domain. And remember, the domain is exactly the same thing just about as the vertical asymptote. We just say it's going to be x is all real numbers except it can't be 0. So we can really simply just write that as x can't be 0. And then range, we can do the same thing where we'd say it's going to be everything but the horizontal asymptote. So we say the range is y cannot equal -3. That's our first example. Let's go on to the next one. Alright, so this one we've got our a value is again 1, h is 3, and then k is going to be 2. So I'm going to, this time, instead of doing the transformations over here with the points, I'm going to go ahead and draw out the asymptotes first and write those out. So my horizontal asymptote and my vertical asymptote. We'll start with the vertical asymptote. We say that's x equals -h. Well, -h in this case is going to be -3. So I can go ahead then and draw in when x is -3, which is going to be right here. We'll go ahead and draw that vertical asymptote. The next one we want to look at is the horizontal asymptote, and that's just y equals k. And in this case, my k value was 2. So we'll go ahead and draw in when y equals 2, that's right here, our other asymptote. So you can see, again, this point right here is -3, 2, or -h, k. That's the center of our asymptotes, just to kind of get back to that definition. Now let's find out exactly where the couple of points we need really should be. So when my h is positive, that tells me I'm doing the opposite. I'm moving everything to the left, so I'm subtracting 3 from each of these, and that gives me -1 minus 3 is -4. 0 minus 3 is -3, and then 1 minus 3 is -2. Oops, -2. With the k values, that's adding 2 to all the y values. -1 plus 2 is 1. We can't add anything to undefined, so we skip right down here. And then 1 plus 2 gives us a +3. So the points I'm going to graph are -4, 1. The -3 undefined, we already did that. That was our asymptote, right? That was the vertical asymptote, so we don't need to worry about that again. And then -2, 3 is my other point. So -4, 1 is going to be right here. And then -2, 3 is going to be right here. Let's go ahead and draw the curve. Alright, so now that we have that, we can go ahead and write out our domain. Again, it's everything except the vertical asymptote for x, so x cannot equal -3. And then range, we say it's everything except our horizontal asymptote. So y, that's not a 4, that's a y cannot equal 2. That's it. Okay, so the next examples we're going to look at are going to incorporate a value for a. We'll see how we handle those. Alright, so with this example, I do want to move a little bit faster. Let's go ahead and start by identifying a, h, and k. Again, we have a equals 4. We have h equals a +1. And we have k equals a -3. So h and k, again, are going to be the locations of my vertical and horizontal asymptotes. So vertical asymptote, we know that's x equals -h. In this case, that's going to be -1. And then my horizontal asymptote is y equals k, which in this case is -3. I'll go ahead and draw those in with my dotted lines. Vertical asymptote when x equals -1, and horizontal asymptote when y equals -3. Okay? So now let's go ahead and plot the points and see, okay, we've got this value of a. As I mentioned before, we're just going to estimate how far away each of those points are. We still need to have at least one good solid point to give us an idea of what this should look like, okay? So let's go ahead and do that. I'm going to subtract 1 by my h from each of the x values. So that gives me -2, -1, 0. Follow order of operations, so that means I'm going to multiply by a first to all of the y's. That's -4, and then +4, and then I'm going to subtract 3 from each of these. So -4 minus 3 is -7, 4 minus 3 is 1. So let's go ahead and plot these points that we want to look at. We have -2, -7. We have -1 undefined. Again, that's my vertical asymptote, so that one's already done. And then I have 1, 1. So let's plot those and see what it looks like. So here is 1, 1, and then -2, -7. Here's 4, 5, 6, and 7. And there's -2, -7. So you see here again, this is a little bit wonky. I can't just draw it going straight up. This is where we say that the larger the asymptote, the further everything is away from my curve. So I'll go ahead and make a quick sketch of what this should look like. Give me a second. Okay, so there's our curves, and you notice again that they are further away from the asymptotes. This distance here diagonally from the asymptote is further away, and that's determined by the A value being 4. That's how we really see the vertical stretch. Okay. Again, pardon these being so crude and rough. I'm having to do this with my mouse, so it's kind of tough to get those to be nice, smooth curves, but you do want to make sure they are nice, smooth curves, okay? All right, so the next one is the last example, and I want you guys to try and do that on your own, and I will post it up on here so that way you can see what it should look like at the end, okay? So hopefully this is what you guys ended up getting as well for your graph. I want you to notice too, this time I've got my curve in the top left quadrant of these asymptotes and the bottom right. If we were to look back at the previous examples, all of these other ones had them in the top right and bottom left. So the vertical reflection that we saw right here really just impacts which quadrants these are going to be in. So if ever you got a negative A, you're always going to have a curve in the top left and another one in the bottom right. Okay, finishing up with domain and range, we have x cannot equal -1 and range cannot equal y cannot equal -3. That's simple. Okay, go ahead and get started on your assignment, guys. Thanks for watching. Have a wonderful day, and I will see you next week.